Hello everyone. In this video, we are going to talk about finite automata, and we focus this week on deterministic finite automata. So what is a finite automata? So informally, actually, finite automata is going to be a state diagram that shows you all the possible states in a machine and all the transitions between these states. While this machine can actually read some input, which is going to be a sequence of symbols from the input. So it will be, something like this. We have your machine, your finite automata is going to have two parts. One part, a unit, which we call it actually a finite control, or this is going to be your finite unit, and there is going to be some tape that you can actually assume that your input is going to be written on a tape. That tape is going to be a one-way read-only tape, which has been divided to some cells. Over each cell, there is going to be one symbol of the input. This is important to know that the finite control has only have this control to read the input in one way, and it cannot actually just write anything on the tape. It can just read from the tape. So your finite control is going to actually have all of the states. It also have access to this head that reads the input from a tape, and we should just think about it in this way, that this is like a small CPU that can actually do some computation. Basically, it does have some only states. It also have access to some reading the input. It doesn't have any memory, actually. You should think about it in this way, that there is no actual memory except the states that has been written in this finite control. So what we have in this finite control, in this processing unit, in the processing unit, we are going to have a finite number of states and all the transitions between them. One thing that is very important here, crucial here, is that the number of a state for us is finite. That's why we call it actually a finite automata, because the number of states that we can have in this finite control is finite. So this is an example of a finite state. Remember this example from the last week. This is a state diagram that represent, a pattern matching system that checks, that recognize the pattern then in the input. It actually has a start state. It started at some specific state. Always when you actually turn on your machine, it is going to be in a state, right? That is going to be the start state. And then whenever you see a T, it goes to this state that just show you that you just saw one T, and then whenever you saw an H, it goes to this state that just tells you that you just saw a TH, and so on. So these are the states, and these are the transitions. Okay, so the transitions actually would show that whenever you actually see T in the input, you read T from the input, and your finite control from this state goes to this state. Okay, so at each position, your machine is going to be at one of these states that has been actually mentioned in your finite control. So your machine is going to be a set of states. All the transitions between them has been set, and it has an access to a head that reads the input, and by reading each input, it just change the state, that the current state that the machine is at. Okay, so what is important here for us is that finite automata, these type of machine with this amount of computation power, which is going to be only a finite number of states and only being able to read the input once, this type of machines with this much ability, power, they are going to accept a set of languages. That set of languages is going to be called regular languages. So this is important for us, that this machine is very limited in terms of the computational power. It cannot read the input more than once, and it cannot have access to an infinite amount of memory. Just the number of states that you have in the control, a state is going to be kind of similar to the amount of memory that you can have, and it is going to be finite. We have two different types of finite states. One is going to be called deterministic, the other one non-deterministic. This is important, that deterministic and non-deterministic finite states are going to have the same power. They are going to, both of them representing the same set of languages that we call them regular language. Next week, we are going to cover non-deterministic finite states. This week, we are focusing on deterministic finite states. The difference between deterministic and non-deterministic finite states is that in a finite state, which is a deterministic finite state, at each step, at each situation, the machine will be exactly in one state. But in non-deterministic finite state, it is possible that after, for example, a specific input string, you can actually say that this machine can be in this state or in this state. I know that it might not very, very clear that what does this mean, but I'm going to show you some example, then it would actually makes it more clear that what does this non-deterministic finite state means. But just the non-deterministic finite state is about the design of the machine, but the coherent the core of the power of the machine is the same. That is going to be that deterministic finite state. It's just a different way to design the machines. I will actually talk about the non-deterministic finite states next week. So let's just leave it here. Okay, let me show you an example of a deterministic finite state. This is an example of a deterministic finite state. We have three states here. Usually we actually represent that start states with an incoming arrow. Sometimes people just start writing on it that it is a start, or whenever just you saw the states that it has an incoming arrow from actually nowhere, this is going to be, that state is going to be your start, the start states. In any deterministic finite, basically in any finite state, one or actually even none, some of the states might have been, shown by double cycle. These states are going to be the accepting states. Okay, so in this state, we have a start state, we have exactly one final state or accepting state, and the other two states are non-accepting state. And you might actually now ask that how does this machine work, and how it is going to actually, when it reads an input, what would happen on this machine. Okay, so just assume that you have your input have been written on a tape, just something like this. Whenever you read the first input symbol at the very beginning, you will be at the state Q0, the start state, right? And at the state Q0, if you see a 0, you should look at the transition. What does the transition over 0 tell you? The transition over 0 tells you that you should go to the state Q1. Okay, so your current state now is going to be, your current state previously was Q0, then now you will be at Q1. Let me just erase this one. Then you read the next symbol, it is going to be 1. you are at Q1, the transition tells you that you should go to Q2. So from Q1, you go to Q2. Now you are at a state Q2, your next input symbol is going to be 1. The transition over Q2 tells you that over 1 you should stay at Q2. The next symbol is 0, and the transitions tells you that you should stay at Q2. And now it is clear that when you reach to Q2, in this example, you would never leave Q2 over all the possible inputs, which is going to be 0 and 1. You will stay at state Q2. Okay, this is exactly how we read an input over this example of a deterministic finite state. And what would happen is when you reach to the end of the string, you will be at the state Q2. This is important because this is the meaning of those strings that you accept. If you read the full string, the full input string, and at the end you will be at an accepting state, you would say that you accept the string. So this string will be accepted. This string of 0, 1, 1, sorry, 0, 0 will be accepted by this finite state. For example, some other states might be, some other inputs might be rejected. Something like, for example, 1, 1, 0. You can see that if you have a string like this, what would happen? You will be at Q0 first. Over reading the first one, you will stay at Q0, all right? Reading the next symbol, it is going to be 1. Again, you will stay at Q0. What I'm actually showing here is not going to be a deterministic finite state. I'm just actually showing you that in which state you will be after reading each input symbol. And then you will read the next input symbol, which is going to be a 0. From Q0 over 0, you will go to Q1. Now you see that you are at the end of the input string. You read everything, right? And you are at a state Q1, which is not an accepting state. So if you pass this input string to this finite state, it will reject the input string. It's just like your finite state, basically just return yes, no. You pass an input string, it tells you that this input string is accepted, this input string is rejected. And this is exactly what we are looking for. Remember, we said that every problem for us in computer science can be represented as a set of strings defined over an alphabet. So finite states that we are going to design basically are going to represent those problems. They are going to represent that set of strings. So any string that you pass to this finite state, it does tell you that either it belongs to a specific language or not. If it belongs to that specific language, it tells you yes. If it doesn't belong, it returns you no. So basically, finite states are going to represent each finite state that you design is going to represent a language. That language is going to be, the language that will be represented is going to be the set of all the input, all the strings that will be accepted by this machine. Okay, I have been talking over this slide and this example a lot. Here we have actually just, I have summarized what I explained there. It tells you that you should start from a start state, just read over the input strings one by one, and over each symbol from the input, just follow the transitions, and at the end, if you reach to an accepting state, you will accept the string. If not, you will reject the string. And it is important that you should read all the inputs, all the symbols of the string. If you haven't finished the inputs in the string, if the finite state cannot finish all the symbols from the input strings, it will crash, and you can assume this means that the finite state is telling you that the strings has been rejected. Okay, so Now let's get back to actually this example. Um, Now that we have actually been talking about the languages, now we can actually see some pattern here. What type of strings, what actually binary strings will be accepted by this finite state automata? You can see that if you just play with a couple of examples, you will see that for any input string that you pass to this finite state, if the input string has a pattern 0, 1, it will, starting from the Q0, it will end up to Q2, right? And it will never actually leave Q2 after that. So something which is essential about this finite state is that it will accept all those binary strings that has the pattern 0, 1. So that's it. This is going to be the definition of the language of this DFA. The language of this DFA is going to be the language of all binary strings that has the pattern 0, 1. Okay, and basically any other input, any other binary string that you pass to this DFA will reject that, right? If you don't have the pattern 0, 1, you would never be able to reach to Q2, and so this DFA is going to represent this language. Let me show you now the formal definition of a DFA. Okay, we define a deterministic DFA using a 5-tuple, 5 different components in a deterministic finite state. The first component is Q, which is going to be a set of states. In the previous example, this is going to be Q0, Q1, and Q2. So it tells you that we have a set of states. This is important. The number of states is going to be finite. You are going to have an alphabet. The alphabet tells you that what are the possible symbols that you can read from the input tape over the input tape. Again, you know that the alphabet should be a finite set of symbols. One of the states is supposed to be marked as a start state. Usually we call it Q0, but the name is not really important. Just know that one of the states should be marked as a starting state. Your machine should start from that state. You should have a number of finite state. Be careful, you might actually not have any final state in your deterministic finite states. So this is going to be a subset of states that we call it actually a final or accepting states. We show it with F. And there is going to be a transition delta, I guess we call it, this symbol. So this shows you the set of all the possible transitions that you have in your deterministic finite state. So this is going to be a function basically that maps a pair of one state and one input symbol, and it maps it to another state. So be careful, this is a deterministic finite state. So from over this mapping Q, for example, from a specific, if you are at a specific state Q, if you see an input symbol S, you will go to another state Q prime, one of the states that you have. So yeah, intuitively, it just actually tells you that if you are at a state, this transition tells you that if you are at a state Q, the input symbol is S, you will go to the state Q prime. Okay, you can represent a DFA either using a state diagram this way, which is very visual and makes it much easier to read and understand for us as human, or you can represent it as a table. On the computer, definitely, when we are in fact simulating a DFA, if you can actually write a computer program, whatever, you can design a program to simulate a deterministic finite state, it will be represented using a table that the rows are going to represent the states, the columns are going to represent all the input symbols, and in this table, it just basically tells you that, for example, at state Q0, if you read the symbol 0, you will reach to a state Q1. How we represent the final state and the starting state, we usually actually again use a arrow to show which state is going to be a starting state, and we just put the star over the accepting state. So here I have one accepting state Q0 that has been marked using this star here. The number of states are going to be 2 states, right? The input alphabet is going to be the binary alphabet. The starting state is Q0, the final state is Q0, and here is the transition table. So you can either represent it this way or this way. Clearly, the state diagram is going to be much easier for us, right? As a human, it's more visual. Okay, so now let's look at this example. What is going to be the language represented by this deterministic finite state? Remember, a language of a finite state is going to be the set of all strings that will be accepted if you give them to this finite state. So, what do you think about this example? You can see that start at the very beginning. If you haven't seen anything, you will be at a state Q0, which is also an accepting state, right? So even if you don't read anything from the input, you will be in accepting. It basically means that epsilon, remember epsilon? Epsilon was a string, an empty string, a string that doesn't have any symbol. So empty string is going to be in your language. This is the first thing that you can understand. Then you will see that if you see a couple of ones without any zero, all of those ones are going to be in the language. So basically, if your input string doesn't have any zero, it will be accepted. What else I can see is that if I see a zero, if I am at Q0 and I see a zero, I will go to Q1, which is not accepting. So seeing 1 0, a single zero, is going to make your string unaccepted, right? It will reject your string. But it's actually, you can actually make it accepted if you see another zero. And by looking at this diagram, you can see that this zero doesn't need to be actually the number of those zeros, those 2 zeros that you need to read doesn't need to be sequential. You can actually have a couple of ones in between and again another zero. So this pattern that you can see here is forcing me to have whenever you see a zero, you should see exactly one other zero to make your string again accepting. Okay, so this pattern here tells me that all the string that has even number of zeros are going to be accepted. And there is no actually restriction over where those zeros have been located. The only thing that this finite state cares about will be the number of zeros, and either if it is even or not. If it is even, it will be accepted. If it is odd, it will be rejected. And you can see that all the previous observation that we had will be satisfying this definition. So this finite state is going to accept all the binary string that has even number of zeros. Okay, so I have another question for you. Is this finite state deterministic? And if yes, why it is deterministic? Whenever, remember, I actually define the definition of deterministic finite state as it is going to be deterministic. It basically means that at each situation, whenever you are reading any input string, at each step, at each time step, your machine should be exactly at one state. This machine is going to be a deterministic finite state. And the reason is that you basically, to be able to check if a machine is deterministic or not, you need to just check that two things. First, you should exactly have one starting state, right? And the second is that at any of the states, for any input symbol, there is going to be exactly one transition. For example, you are at a state Q0. For the input symbol 1, there is only one transition. That transition tells you that at Q0, by seeing a 1, you should stay at Q0. The other input symbol is going to be 0. At Q0, by seeing a 0, you go to a state Q1. So for a state Q0, for each input symbol, there is going to be exactly one transition. And the same for Q1. For 1 and for 0, there's exactly one transition. So that's enough to make this a deterministic finite state. Let me show you a non-deterministic version. Look at this. Is this a deterministic finite state yet? You can see that we have one starting state, that's good, but at Q0 for the input symbol 0, there are two transitions. One transition tells you to stay at Q0, the other transition tells you to Q1. Okay, now this finite state that you can see here is going to be called a non-deterministic finite state because you have a state that over one input symbol, there are more than one transition for us, right? So if you are at Q0 and you see a 0, you can either stay at Q0 or you can go to Q1. So now this exactly is that situation that I'll tell you that at any time step, you should be exactly in one state. But using this finite state, it is possible that at some point you will be at two different states. After seeing 1, 0, you can stay at Q0 or you can go to Q1. Okay, how about this one? Is this a DFA? You can see that at each state, over each transition, there is going to be exactly one, over each input symbol, there is going to be exactly one transition. Over Q1 and the input symbol 0, there is no transition. You can see that in the table also it shows that as an empty set. Over Q1 and the input symbol 0, there is no transition. This is going to be a DFA, but it's just missing a transition. Missing a transition doesn't actually mean that it is a typo. Basically, theoretically, for us, whenever you see that there is no transition defined here over Q1, it means that if you are at Q1 and your machine see a 0 in the input, your machine is going to crash, right? Because there is no transition. No transition has been defined. So basically, your machine is going to reject the string. That string will be rejected by this finite state. And this is just a theoretical definition, but basically here, when you say that there is no transition over 0 on Q1, it just means that the machine is going to reject that input string, whatever it is. Although, mechanically, if you wanted to create a finite state, because you can create a machine for a finite state. So mechanically, if you create a finite state, in that case, instead of actually allowing your machine to crash, you would probably add some other states that from Q1 over 0, you would add another states, I don't know, Q2 over whatever, and here your machine would stop. So whatever is the state, you will actually just simulate that crashing thing that we said here. So basically, this is the same. This machine, and if you have this new state Q2 or not, they are going to be the same. They are doing exactly the same thing. They are not representing two different machines. I have actually written down all of these, discussions that I have had. Okay, so remember when we talked about a finite state, and basically in this course, whatever machine we talk about, what we care about is the language that will be that will be represented by that machine. So we define a type of machine with some ability that they are going to be called finite state machines. They are representing a language. And what is that language? That language is called those set of languages, and they are called regular languages. So we say that if a language can be represented by a finite state, it doesn't matter if it is a deterministic or non-deterministic finite state. Basically, deterministic and non-deterministic finite states are going to represent the same power. They're just different representation. So both of them are representing a set of languages. Those set of languages are called regular languages. It is important to know that just like, kind of similar to programming, that for a single problem, you can have different type of solutions, different type of programs. You can have written, I don't know, 100 different programs that solve the same problem. Here you can create different finite state to which all of them actually represent the same language. Uh, Basically, those languages are important for us, not exactly the machines. As long as we know a language can be created using a finite state, that's enough for us to say that, okay, this language is going to be regular. So one thing that is important about regular languages is that regular languages are going to be the simplest set of problems that we can solve in computer, and we can actually efficiently solve them. Here, the terms efficient that I'm calling about is an informal definition. And basically, when I'm saying efficiently we can solve them, it basically means that by only reading the input once, without having access to a memory, only those finite state memories that you have, you can solve the problem. This makes it actually, it means that the problem is very efficient. Later on, we will see that there are some problems that you cannot solve them using this amount of power. You need either to have access to some memory and infinite amount of memory, or you would, in some cases, you also would need to read the input string more than once. You can now here see that you are reading the input strings in the finite state only in one pass. You never actually be able to go back and reread any input symbol. If you read it, that's it, it's gone. So these are just some limitations about the finite states and show that how efficient the finite states works, and we can solve the problem with them. Okay, so I think we have already talked about this, the fact that, yeah, the regular languages are going to be represented using deterministic finite states. And for example, this is important. Some, regular questions, I shouldn't probably use the term regular. Some common question that I would ask during this course is that I would give you a language and say that, okay, is this regular or not? Is this context free or not? So if I gave you a language, if you can create a DFA for that, if you can create a finite state for that, that's enough to prove that that language is a regular language. And basically, regular languages are going to be very useful for us You should probably have already noticed something about this name, regular languages, and for example, regular and the term regular expressions. Remember, I'm sure that you have used regular expressions in your programming, in different programming languages, or when you are actually typing something in the command line, the terminal, um, right? Yes, regular expressions also are going to be some representation of regular languages. Basically, when you write a regular expression, the computer will convert it to some simulator, like a DFA simulator, and then execute it. So yes, regular expressions are going to also to be another representation of regular languages, and they are equivalent to deterministic finite states. We will actually talk about regular expressions, I think, the third week or the fourth week of the semester. I'm not quite sure now. Okay, let's see actually more examples here. These two finite states, these two deterministic finite states, are both of them going to represent the same language. Remember, this was the first, the right one was the first example that I showed you, which represent a set of strings, binary strings with even number of zeros. This DFA is going to accept exactly the same language. You can just see that I have more states, but this DFA exactly represent the same language as the other one. Although you should probably just notice that, of course, I would prefer the simplest form if it is possible to get that. So we say that these two DFAs are going to be equivalent. Just as an example, you might, this finite sets, both of them are going to accept all the binary strings with even number of zeros, including zero. So empty string is going to be in the language as well. So now, as an exercise, just try to modify it, create a DFA that accepts all the binary strings with even number of zeros, which is greater than 0, so greater than or equal to 2. One way to write it is I would make Q0 not an accepting state, and then if you see 1, you would stay because you haven't seen any number of zeros. By a 0, I'm going to Q1, and from Q1, I would need another state to represent the accepting situation. Let's call it Q2. If you see 1 over Q1, you would stay here because you haven't seen even number of zeros yet. In Q2, if you see 1, you would stay because the number of zeros are going to be even yet. But if you see a 0, you would go back to Q1, and if you need to see another 0 to go back to Q2. So this is going to be, a sample solution for this exercise. So let's see another example here. Build a DFA for the following language, the language of all binary strings that contains the substring 1, 1. Okay, basically, to be able to design a DFA, I cannot actually give you a complete approach that, okay, follow these steps and you can design a DFA. You can see that designing finite states are going to be similar to solving a problem. So you should, it is a problem solving approach. But I can give you some, hint that how to approach a problem at the beginning. Later on, when you actually see more and more examples, you will get used to it, and probably this you don't really need these steps. But now, these hints are going to be helpful. When you are designing, when you're approaching a problem and you wanted to design a DFA for that, you should first think about the states that you need, and write down some definition for each state that formally we call it a state invariant. If it is such a thing, I will be in this state. If this is the situation, I'll be in this state. And then after you define all the possible states that you need, not all the possible states which are possible, basically only those specific situations that you need. When you are defining your states, just care about the situations that you need, you really care about them. And then mark which state is going to be a starting state, which state is going to be the final state. During these steps, you might actually notice that, okay, I might need more states. And then at the end, you will add all of your transitions. I am telling you, this doesn't mean that you cannot go back and modify in your steps. So let me actually show you that what would happen in this case. We wanted to actually design a finite state to accept all the binary strings that has the input, the pattern 1, 1. One thing that the number of states that I need here, I'm not quite sure how many yet, but I can write down a couple of states, and then I will actually show you that they are going to be enough or not. I would need to add more. The first thing that I should probably think about is that I would need a state to show that I haven't seen any string 1, 1. So let's actually just write a state for that, name for that, that represent that, okay, I haven't seen the pattern 1, 1. And I haven't actually, the previous input symbol that I have seen was not a 1. So basically, when you have a pattern 1, 1, it means that you are caring about two things that sequentially they both of them are going to be 1, right? So if I have seen a 1, it means that I have actually done halfway, right? It's going to be different than when you haven't seen the previous input string that you have seen is going to be 0, right? So I'm going to write down here as well that I haven't seen the pattern 1, 1, and the previous symbol was not 1. Okay. Another state I would need is that, for example, I haven't seen 1, 1 yet, so it's not going to be, I will not be in an accepting situation, but I have seen exactly 1, 1, and it was exactly the previous input string. Sorry, so again, the Q1 this time is going to be, I haven't seen the pattern 1, 1, but, or you can just write it as and, basically, because it doesn't really mean, and the previous symbol was 1. Okay. And another set that I definitely need is that I have already seen the pattern 1, 1. And just like the previous DFA that you had, if you have seen 1, 1, you probably don't need to go anywhere else. So you can actually stay there. So we would say that I have seen at least one pattern 1, 1. Okay. Do I need more states? You know, it is very likely that when you are designing your actually the number of the states that you need, it is always possible that you're missing something, right? You might not actually think about everything at this situation, but don't worry. I started actually writing which one is going to be accepting, which one is going to be the starting, and then added all the transition. Then you can come back and modify. You might actually notice that, okay, no, I'm missing here. I would probably need another state to complete it. So don't worry, you can actually just come back and, touch up the states, change the definitions, or add more things about it. So this is kind of, at a very first cases, examples that you solve, you might not be master, of course, but after a couple of examples, you would know what to do. So it is clear here that this one is going to be the starting state and this one is going to be the accepting state. All right, so this case, this is going to be, okay, Q0, the starting state. You haven't seen the pattern 1, 1. I'm going to actually write down the state diagram and add the transitions. If at Q0 you see a 0, it means that you haven't again seen 1, 1, and you haven't seen the 1 as this state is not going to be 1, so it would result in a staying at the same state, right? But if you are at Q0 and you see a 1, you can go to a state Q1, right? Because it basically means that you haven't seen the pattern 1, 1, but the previous symbol that you saw is going to be a 1. Okay, the transitions for Q1. At Q1, if you see a 0, where should you go? Can you stay at Q1? Be careful. If you are at Q1, you haven't seen the pattern 1, 1, right? So definitely you cannot go to Q2. And if the input symbol that you are reading is 0, it means that you cannot even stay at Q1, because if you are at Q1 and you see a 0, the last input string, the last input symbol that you saw is not going to be 1 anymore. So seeing a 0 made you go back to a state Q0. But if you see a 1 at Q1, you can basically go to a state Q2, because it basically means that you just saw a 1 and now the next symbol is 1, so that's it. You are going to go to the accepting state. You are going to say that I have seen at the pattern 1, 1 at least once. So I'm done with the transitions for Q1 and the transitions for Q2. If I see a 0, if I see a 1, I don't care, because everything that I care about has been done. I have already seen a pattern 1, 1, and I don't care whatever is going to be the end of the rest of the input strings. For 0 and 1, you should stay at a state Q2 and mark it as a final state as well. So that's it. This is going to be the DFA for this language. Here is our design. And we mark the start and accepting state, and we draw the state diagram. Okay, let's see another example. We wanted to build a DFA for a language that has even number of zeros and even number of ones. Okay, what are going to be the states that I care about? What are going to be the situations that I care about? So here, the one thing about this string is that it cares about the numbers, but it doesn't need to actually, you don't really need to count exactly how many number of zeros or how many number of ones you have seen already. One thing that you care is that is the number of zeros that you have seen is even or odd. The number of ones that you have seen is going to be even or odd. So if you think about it, there are going to be 4 different situations that I care about. I can write down one state for each one. uh, even number of zeros, then and even number of ones. Another state is going to be, okay, even number of zeros and odd. You excuse my handwriting, it's just terrible. I know. And it would be even more terrible when I'm writing on my iPad. Of ones. Q2, even number of zeros. Sorry, we are done with even zeros. Odd number of zeros and even number of ones, and Q3, odd number of zeros and odd number of ones. So you can see that all this, the situation that I care about is going to be these situations. There is no more situation that I care about, and I really need distinct state for each of these situations. So which one is going to be the accepting state? You should always think about, sorry, which one is going to be accepting state? Yes, it tells you that has even number of zeros and even number of ones. So this is going to be accepting, okay? And Q0 is going to be accepting. And which one is going to be the starting state? When you are recognizing which one is the starting state, you should always think about the empty string. If you haven't read anything, if you just read the input string, read the input string basically means that you haven't read anything, which is going to be at the beginning, right? If you don't have any zero, any one, which situation among all of these is going to be the correct one, the satisfying situation? Again, it's going to be Q0. You know, it's just accidentally that Q0 is going to be the accepting and the starting state both. It is just in this example, okay? So now we can just draw the state diagram. Q0, it just tells you that it is even number of zeros and even number of ones. If you see a zero, the number of zeros which is even now is going to change to odd, right? So from Q0, reading a zero makes you to have odd number of zeros, but the number of ones hasn't been changed, right? So odd number of zeros, but even number of, so if it is just from even number of zeros and even number of ones, so this is 0, this is 1. By reading a 1 0, you should go to odd number of zeros and even number of ones, which this one is going to be the situation Q2, right? At Q2 with, at Q0, by reading a 1, you will go to even number of zeros because the number of zeros hasn't been changed, but the number of ones is going to be odd, right? So by reading a 1, you should go to the state Q1. Let me just follow. Okay, as I said, Q1 tells you that even number of zeros and odd number of ones. No, I'm done with the transitions over Q0. The transitions over Q1, I can add them. At Q1, even number of zeros and odd number of ones. If you see a 0, you will be odd number of zeros and odd number of ones. Which state is going to be odd number of zeros, odd number of ones? This is going to be Q3. So over Q1, by transition over 0, you go to Q3. But if you have even number of zeros and odd number of ones, and you see a 1, you will have even number of zeros and odd number of, even number of zeros and even number of ones. So by reading a 1, you go back to Q0. Let's complete the transitions over Q2. Odd number of ones, even number of zeros. Seeing a 0 makes it even number of zeros, even number of ones. Now you actually see that the pattern from Q2. If you see a 1, you go to odd number of zeros and odd number of ones. At Q3, you are odd number of zeros, odd number of ones. So by seeing a 0, you go to even number of zeros, odd number of ones, which is going to be even number of zeros, odd numbers of. So by seeing I made a mistake here, I think. Q2 was odd number of zeros and even number of Q2 was I think odd number of zeros and even number of ones. So if you see a 1, you go to Q3, right? At Q3, if you see a 0, you will go to even number of zeros and odd number of ones, which is going to be Q1. And if you see a 1, you go to odd number of zeros and even number of ones, which is going to be Q2. Sorry. You can see that you can easily go wrong if you don't pay a full attention when you're drawing the transition. Yeah, this is going to be our deterministic finite state in this case. Here I've written, actually documented everything here, but probably the states is not exactly the same as the states that I have written here. I mean, the names are not the same, but the number of states and the concept is exactly the same. And the final example for this part of the lecture, I'm going to create a DFA for, you see this is a slightly different, I have used a different alphabet to show you that not always we use a binary alphabet, but anyway, in this case the alphabet has 3 symbols, A, B, C. Okay, I wanted to create a DFA that accepts all the strings with at least 2 number of zeros. So this is important that then those number of zeros, the definition of the language tells me that I just care about the number of C's, and I care that I have at least 2 number of C's, and I don't care that, for example, these 2 C's are going to be sequential or not. So for example, something like C, A, B, B, C is going to be in the language, yeah, because it has at least 2 number of C's. So how many states we would need and what are going to be those states? Very similar to the first example that we solved. Okay, let me actually write down a couple of states that I'm thinking we would need. I need one state that shows that I haven't seen any number of zeros, because here the definition of the language tells me that we care about the number of C's. We basically don't care that how many A's or how many B's we have seen. So the definition of this state is going to be I haven't seen any number of C's. So haven't seen any C. And Q1 is going to be saw exactly 1C. You can see that I just wrote it as saw exactly 1C, and I don't care that it was the previous, exactly the previous symbol or not. It just tells me that, okay, there was exactly 1C so far, but not 2C's, so we are not going to be at accepting a state yet. And I need another state that say, okay, saw at least 2C's. So this is going to be, if you see 2 or more, all of them are going to be represented by Q2. So here, this one is going to be the starting state, right? If you haven't started yet, it means that you haven't seen any C's as well. So you are going to be at the state Q0, and this is going to be the starting state. Q0. If you see 1C, you will go to Q1. You have to actually write down all the transitions over all the input symbols, right? So Q0 over A or B, you should stay at Q0, right? Because it means that you haven't seen any C yet. At Q1, again, if you see 1C, you will go to Q2. But if you see A or B, you will stay at Q2. And you don't go back to Q0 or anywhere else because you have seen 1C. And at the state Q2, it doesn't matter what you are going to see, A, B, C, you will stay at this state because you don't really care about the rest of the things. You have seen at least 2C's. And I've just marked Q2 as your starting state, as your accepting state as well. So here is the states and the state diagram here. Okay, I'm going to finish this lecture. I think it's been around an hour. In the next lecture, we are going to just talk about this fact that how we can prove if the state diagram that we draw, the finite state that we create, is going to represent the language that we are interested or not.